Okay, and this one, okay, have a lot of similar stuff, but some items with a little bit of an added twist. Okay, it looks like for at least for the first two problems, okay, you're looking at a situation where it looks like we'll be using the property, a first logarithmic property, where you have the base A logarithm of a to the x is equal to x. And for what we have in the case of the first question, okay, so we're looking at the base 6 logarithm of 6. If I look at determining, okay, what the final result is going to be, so you had the base 6 logarithm of 6, and okay, so if you notice we have like base A logarithm of a, had the base 6 logarithm of 6. Okay, so your a value is going to be at 6, and in terms of the x value, you don't have raised power for the exponential base 6, but you'll read this as if it had been 6 to the first power. So the base 6 logarithm of 6 is going to come out equal to 1. And for what we have in the case of the second item, and we have the base 4 logarithm of 1 over 64 . Okay, now for 1 over 64, now 64 is both a multiple and an integer power of 4. Okay, so you've got 64 is going to be 4 to the third. Now, 1/64 is going to be the reciprocal of 4 to the third. And if I rewrite 1 over 4 cubed in terms of a direct exponential base 4, okay, so you have the base 4 logarithm of 4 to the negative 3. Okay, so you have the base A logarithm of a to the x formation. And so that x value, okay, that is going to be negative 3. Now, for what we have in the case of the next item, okay, so you have the base 5 logarithm of 25 to determine. Okay, so you have in this one, okay, so you have the base 5 logarithm of 25, and 25, okay, that one you have to be both a multiple and an integer power of 5, and 25 is going to be 5 to the second. So the base 5 log of 5 to the second, okay, that is going to go to 2. And for the base 2 logarithm of 1 over 32, okay, so you have a reciprocal of a power of 2. Okay, so you got 1 over 32. Now 32 would be 2 to the 5th power. And so here we have here the base 2 logarithm, and the reciprocal of 2 to the 5th is going to be 2 to the negative 5. So back to the base A log of a to the x, and the missing value in this case is going to be at negative 5. Right. Now, in looking at what we have for the next set of items, and again we have for evaluating expressions. Okay, so we have base A logarithm of 1/8. Okay, so this would be like base 8 logarithm of 1 over 8 to the first. And just rewriting 1/8 directly in base 8 terms. So 1 over 8 is going to be 8 to the negative 1. So you got the base 8 logarithm of 8 to the negative 1. So the base 8 logarithm of 1/8, okay, this will come out to negative 1. And for what we have in the case of the base 3 logarithm of 81, okay, so 81, okay, is a multiple of 3 and also an integer power of 3. Okay, so with 3, got 3 times 3 is 9, 9 times 3 is 27, and 27 times 3 is 81. So it would take 4 3's to attain a product of 81. And so we have with base 3 log of 3 to the 4th. Okay, and so that output, again, we have at 4. All right. Now, for what we have in the case of the next item, okay, and okay, there's a little bit of a twist on these, especially with parts B and C. Now we have with A, okay, so you got sum of base 9 logarithmic terms, and I'm looking at making it to a single base 9 logarithm. So from part A, so I have the base 9 logarithm of 7 plus the base 9 logarithm of 10, and looking at piecing together, again, addition is going to imply multiplication of the attachments. So we have a base 9 logarithm of 7 times 10, and so we'll come out to base 9 logarithm of 70. Okay, so 70 is going to be the missing value in this problem. Okay, now for what we have in the case of part B, okay, you could look at this from either of two perspectives. Okay, now I'll just move over here. Okay, so we have for part B, we'll say that X will be the missing value. And for the setup, okay, so I can say that I can say I have a base 4 logarithm of X minus the base 4 logarithm of 5 is equal to the base 4 logarithm of 3/5. Okay, what I mean by this, I can either combine these logarithmic terms together into a single logarithm, or I can expand what is on the right. Okay, but regardless of whatever I have, okay, X must be positive. Okay, so you either combine on the left or expand on the right. Now, so I'm just going to expand on the right. So here we're going to have the base 4 logarithm of X minus the base 4 logarithm of 5, okay, is equal to the base 4 logarithm of 3 minus the base 4 logarithm of 5. Okay, and if you notice, we have identical logarithmic terms on both sides. So if I were to add the base 4 logarithm of 5 on both sides, so we have these terms would cancel. So I have the base 4 logarithm of X is equal to the base 4 logarithm of 3. And if you notice, I have single terms, just like before with exponential equations with a like base. If I had single terms and the same exponential base on both sides, I can set the powers equal to each other. Well, here we have individual logarithmic terms in the same base, and I can go ahead and set the attachments equal to each other. And so it's going to follow for the missing value. Okay, we're going to have x equal to 3, so x will be the result for what we have in the case of part B. Okay. And for what we have for part C, okay, so you have a base 6 logarithm of 25, and if I rewrite this in terms of base 6 logarithm of 5, okay, so I have a base 6 logarithm of 25. And if I write in terms of where 5 is going to be the attachment, so 25, again, you have both a multiple and an integer power of 5. So 25 is going to be 5 raised to the second. Okay, and again, looks like we're going to be looking at converting powers into coefficients. So the base 6 logarithm of 25, okay, this will become 2 times the base 6 logarithm of 5. Okay, and then we have for the next item, and we have in question number 5. Okay, it says to use the properties of logarithms to expand log, or the base 10 logarithm of z times y to the 9th, and it says should not have any exponents and assume that all variables are positive. Okay, so we have, looking upon this particular term, okay, so I have log of z times y to the 9th. Okay, and looking at expanding, okay, so we have in the attachments, okay, have the operation of multiplication, and multiplying is going to imply addition when writing and expanding out into separate logarithmic terms. Okay, so we'll have the base 10 logarithm of z, and we have plus the base 10 logarithm of y to the 9th. Okay, and again, I have an exponent with 9, and I just convert this into a coefficient. So this will come out to the base 10 logarithm of z plus 9 times the base 10 logarithm of y. Alright. Now for what we have in the case of number 6, now this one, kind of a different one with its own special twist. So we have another base 10 logarithmic term, and we have z to the 3rd, and we have all over the square root of x to the 5th times y. And say if I look at writing in terms of non-integer powers, what we have in the radical, okay, so I have base 10 logarithm of z to the 3rd. I'm just going to mention now, if you notice in the denominator, okay, so I have the square root of x to the 5th times y. Okay, and whenever you're dealing with the square root, you're dealing with 1/2 in terms of an exponent. Okay, so you have the square root of all of x to the 5th y will be the same as taking x to the 5th times y and raising to the 1/2, and the 1/2 degree is going to affect both x to the fifth as well as y. So we're going to have in the expanding, we have like x to the fifth, its own factor is going to be taken to the 1/2 degree. And guess what? We have with y, that is also to the 1/2 power. And we have with the power property of exponents. Okay, so this will come out to x to the 5/2 times y to the 1/2 power. So just to mention here. Okay, so in the rewrite, so I'm going to have the base 10 logarithm of z cubed, and this is going to be all over x to the 5/2 times y to the 1/2. And so just looking at expanding, okay, so I have at the top, so I have base 10 logarithm z to the third, and with both the x and the y factors in the denominator, okay, each of their own respective base 10 logarithmic terms will be negative. So we have minus the base 10 logarithm of x to the 5/2, and we're going to have minus the base 10 logarithm of y to the 5/2, excuse me, y to the 1/2. And just looking at, once again, converting from powers to coefficients. And so we're going to have 3 times the base 10 logarithm of z minus, we have 5/2 of the base 10 logarithm of x minus 1/2 of the base 10 logarithm of y. Okay, so that one, a little bit of a tricky one, especially with the clustering of terms inside the radical, but still solvable and expandable. Now, for what we have in the case of item number 7, okay, so we have another expansion case. You have base 10 logarithm so you have 6 times, okay, the square of x plus 5 we have all over the cubic roots of x to the 4th and again, just taking what we have in the radical. Okay. If I rewrite, so I have the cubic root of x to the 4th. Okay, so this will just go to x to the 4/3. So I got the base 10 logarithm. Okay, so I have 6 times, again, the quantity of x plus 5 raised to the 2nd. And it's going to be all over x to the 4/3. And looking at separating, okay, so I got 2 factors in the numerator. And if I look at those first, okay, so we're going to have a couple of positive base 10 logarithmic terms. So I have that of 6, and we have plus base 10 logarithm of x plus 5 raised to the 2nd. Then I'm going to have minus, okay, the base 10 logarithm of x to the 4/3. Okay, now in terms of the individual term, where we had the base 10 logarithm of 6. Okay, now 6 is neither a multiple nor an integer power of 10. So in exact terms, okay, the base 10 logarithm of 6 is already simplified. And as for the subsequent terms, okay, we just have to convert the exponents to coefficients. So we're going to have the base 10 logarithm of 6 and a half plus 2 times, okay, the base 10 logarithm of all of x plus 5 and a half minus, okay, 4/3 of the base 10 logarithm of x. And just taking what we have now, okay, so in 8 we're looking at squeezing together, okay, these base 2 logarithmic terms and making into one expression. So what I will do here, okay, so we have from the start, okay, so looking at writing as a single logarithm, okay, so any coefficients I have, I can express as powers. Okay, so I have looks like the base 2 logarithm of w to the third, and we have minus, okay, the base 2 logarithm of y to the 1/5, and we have plus the base 2 logarithm of x to the 4th, and looking at putting together, okay, so I got the coefficients converted and just compiling together. Okay, so w to the third stems from a positive logarithmic term, so that's going to go at the top. Y to the 5th comes from a negative, so this will be situated on the bottom. And we have plus base 2 logarithm of x to the 4th, so x to the 4th will go on the top. So this will be your answer, and if there could be any other way to express this, this would be like taking the base 2 logarithm of w cubed times x to the 4th and y to the 1/5. This would just be the 5th root of y. Okay. All right, and now just for what we have in the case of number 9, okay, we got this time a logarithmic equation. And again, when we looked at exponential equations or looking at reducing logarithmic terms, I took the base a logarithm of a to the x is equal to x. Now for logarithmic equations, okay, now the close relative of base a logarithm of a to the x is a to the base a log of x is equal to x. And we have, in the case of number 9, okay, so we got the base 9 logarithm of x is equal to -2. And if I take care of the base 9 log appearance, I can treat both sides as powers, to which the exponential base 9 is going to be raised. So we have 9 to the base 9 logarithm of x is going to be equal to 9 to the -2. So the left hand side becomes x. X is equal to 9 to the -2. And it says to simplify your answer as much as possible. And what that would mean, okay, we have for 9 to the -2, this would be the reciprocal of 9 to the 2nd. And 9 to the 2nd is 81. So 9 to the -2 is going to be 1/81. and that'll be your simplified result in this case. All right, and then we have just taking what we have now for number 10. Okay, and we have a similar type of scenario, and here we have the base 4 logarithm of the quantity of 3x minus 8 is equal to 1, and using this property, so now it is going to be the exponential base 4 they're going to use, treating both sides of this equation as powers. Okay, so the left hand side becomes 3x minus 8, and the right hand side, okay, 4 to the first, that is going to be at 4, and so we have a two-step linear equation, and if I add 8 to both sides, okay, so we're going to have 3x is equal to 12, and we'll have the x's equal to 4. And let me just mention, if I get too far ahead, okay, so from this one, okay, x had to be positive, and likewise 3x minus 8, that had to be positive as well. Okay, and with x at 4, 3 times 4 is 12 minus 8 is 4, so 3x minus 8 was definitely positive. And I'm going to go ahead and squeeze in number 11. Okay. And for this one, okay, so we got negative 6 times the base 4 logarithm of 5x is equal to negative 12. And you can make life simpler, and one might pose the question, can you divide this whole equation by the coefficient that is in front of the logarithmic factor? In this case, yes. Okay, so if I divide out, I'm going to have that the base 4 logarithm of 5x is equal to 2. And once again, we have for applying the exponential base 4 just to take care of the base 4 logarithmic appearance. So the left hand side is going to be at 5x, and we have that 5x is equal to 16, and with division by 5 we have that x is equal to 16/5, which you can also write as a decimal at 3.2. And again, 5 times 3.2 is 16, so 16 is a positive value. Okay, so we do have x to be at 3.2 as the solution.